Hello. Today we are going to learn how little g, the acceleration due to gravity, was first determined. And when I say first determined, it was Galileo Galilei who determined little g experimentally. Unlike some of the legends, he did not drop things off the Leaning Tower of Pisa, which was Pisa, which was the highest building at the time, about 9.5 stories. What he actually did was he rolled balls down inclined planes. Because there was less friction, he could do better timings because it takes longer for a ball to roll all the way down the inclined plane. And that's how he did it. He determined it to be, as we know today, 9.8 meters per second, or 9.8 meters per second squared. Now the formula that is behind me is distance equals 1/2 at squared. That is a general formula that you have been learning about in the course. If we rearrange this to solve for acceleration, we come out with a equals twice the distance, something goes, divided by the time squared. Now in front of me here I have what is known as an air track. It is basically an inclined plane where air is forced out of these little holes here, which you do not see, in order to elevate a little glider so that it does not touch the aluminum plane here. It floats on a little column of air, which basically has almost no resistance. I have an assistant with me, Carolina, and she's going to introduce herself by coming into the frame. She's going to turn the motor, the pump motor, on and off that forces the air out of the holes. And when that happens, it will make a little bit of noise, so we're going to turn it on and off. Let's turn it on just for a few seconds so I can show you how this floats. Almost no friction at all. And so I can feel the air coming out of the little holes. Now it stops because there's no air coming out. Air pucks, air hockey, all works the same way. Now what I've done is determine some of these numbers ahead of time, but I'm going to show you how it is done. We need to know the distance along this track this air puck is going to go, and we need to know how long it takes to do the distance. So I have done this a number of times. The distance measured with a meter stick is 1.38, I think I have it right, 1.38 meters, or 138 centimeters, but we're going to use meters and kilograms and seconds. That is the length that is going to be from here, as far up as I can put it, to the very end. When the front of this car goes to the very end, that's 1.83 meters. Now I should also say that the hill is inclined. If there was no angle, it wouldn't go anywhere. But we've put a couple of weights on the end of this so that it is inclined. Now we need to know how much it is inclined. In other words, this angle here, theta, I call it. It has come out to be 0.65 degrees. It looks a little bit more than that on this table, but the tables are uneven. So it is only 0.65 degrees, but that's enough to let this go downhill under virtually no friction, and we can measure the time. The time turns out to be about 5 seconds. So we're going to show you how that was determined. I'm going to push this up to the top of the hill, and we're going to measure one timing by turning this electronic timer on. And now we can turn on the motor. There we go. Okay. And that came out right on the button at 5 seconds. That came out right on the button as 5 seconds. That's what we originally had. Now, what you should do, if you're actually doing this experiment, you should take at least 5 readings, timings, and average them together to get more close to what it should be. So your accuracy would be improved by doing that. Now, what did we get? Well, 5 seconds. If we substitute that into that equation, then we would get A equals 0.11 meters per second squared. Now, that's how fast the air puck traveled downhill. What we need to know is how much faster would it go, or accelerating that it would go, if it were just dropping, which is what happens under little g. It's not down a hill, it's if you're dropping. And so we multiply this by a factor. It's going to go slower down the hill than it would be if you just dropped it, okay? The acceleration down the hill is equal to little g times the sine of the angle, theta. And when we measured it, if you remember, theta is 0.65 degrees. How do we get that? Very simple. We measure the differential height of the slope. Like, for instance, how much higher is this than this? And we take the difference and we use the length for the base, and we do a little trig. We use tangent. The height divided by the length of the base on the table, and that will give us, in this case, 0.65 degrees. Not much. Okay, now what we do is we substitute that into this equation. We rearrange it to solve for g, because we want to know what g would be, as Galileo would have found, and he would have used this equation. We substitute 0.65 in there. We have the acceleration down the slope from before, and when we do the number crunching on this, we come out to 9.7 meters per second squared. That's what we get. And of course, I'm going to go off camera with this. All right. Little g is 9.8 meters per second squared. We know that. And if we divide the difference by the accepted value, we were actually 0.1 meters per second squared off from the 9.8, because we got 9.7. Now 0.1 divided by 9.8 to get a percentage comes out to 1.02%. So in other words, by getting 9.7 meters per second squared, we are actually only 1.02% off. And that's not bad. So thank you for viewing the demo. I will be presenting in the course some questions, follow-up questions, and we hope that you understand how Galileo determined little g.